Episode 80, titled Regularization, Ridge, Lasso, Elastic Net as Control Knobs, the goal is to control overfitting by penalizing complexity in model training, because the easiest way for a flexible model to look smart is to memorize quirks that do not repeat. Regularization is the disciplined counterweight. It tells the optimizer that fitting the training data perfectly is not the only objective, and that simplicity has value when the evidence is limited or noisy. The exam cares because regularization is a core concept that appears in many forms, and scenario questions often test whether you can choose the right knob for stability, interpretability, and governance. In real systems, regularization is also a reliability tool because it reduces sensitivity to multicollinearity, high dimensionality, and sparse features, making models less fragile across retrains and drift. The key is to treat regularization as an objective choice, not a magic setting, because it changes what the model prefers to learn. When you understand ridge, lasso, and elastic net as control knobs, you can tune complexity deliberately rather than hoping generalization appears on its own. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Regularization means adding a penalty term to the loss function, so the model is trained not only to reduce prediction error, but also to avoid overly complex parameter settings. The loss becomes a combined objective. Fit the data, but pay an extra cost for large coefficients or complex structure, depending on the penalty form. This changes the optimizer's behavior because it no longer chases the smallest training error at any cost. It must trade training fit against the penalty. The exam expects you to recognize that regularization is part of the training objective, not a post-training adjustment, and that it changes the learned parameters by design. Regularization works best when the problem has limited signal relative to noise, when features are many and overlapping, or when you want stable, defensible behavior rather than brittle maximum fit. It also makes the model less likely to assign extreme weight to rare or noisy features, which is a common overfitting path in high-dimensional data. When you define regularization this way, you understand it as a controlled bias-variance trade-off embedded in the loss. Ridge regression is a regularization approach that shrinks coefficients smoothly but keeps all features, meaning it discourages large weights without setting most weights exactly to zero. The effect is that features still contribute, but their influence is reduced, and the model becomes less sensitive to sampling noise and multicollinearity. Ridge is often a strong choice when many predictors share overlapping information, because it stabilizes coefficient estimates by spreading influence across correlated features rather than forcing an arbitrary winner. The exam cares because ridge often appears as the stability choice, especially in settings where you do not want to drop features, but you do want to reduce variance. Ridge also tends to produce more stable predictions when features are correlated because it avoids extreme coefficient swings that can happen when the model tries to isolate unique contributions that are not truly separable. In practical terms, ridge is a knob for smooth shrinkage, which makes the model less jumpy across retrains. When you explain ridge, you are explaining stability through controlled shrinkage rather than through feature elimination.
LASSO is another regularization approach, but it has a different behavior. It can shrink some coefficients all the way to zero, which effectively performs feature selection. This is valuable when you want a simpler model with fewer active features because it produces a sparse set of predictors that are easier to interpret and maintain. LASSO can be especially useful when you suspect only a subset of features carry signal, or when you want to reduce operational dependencies by limiting the number of required inputs at inference. The exam expects you to understand that LASSO is not guaranteed to pick the true features, especially when features are correlated, because in correlated groups it may select one and ignore others in a way that can feel arbitrary. That selection behavior can be useful, but it must be validated for stability, because small data changes can change which feature in a correlated cluster is chosen.
LASSO is also a governance tool because sparse models are easier to explain, audit, and operationalize, but only if the selection is stable and conceptually defensible.
When you explain LASSO, you are explaining selection as a consequence of the penalty shape, not as a separate algorithmic step.
Elastic net blends ridge and lasso behaviors, combining smooth shrinkage with the ability to drive some coefficients to zero, which makes it useful when you want both stability and selection. In practice, elastic net is often chosen when you have correlated feature groups and also want sparsity, because it can keep groups more coherently than pure lasso while still reducing the number of active predictors. The exam cares because elastic net is the practical compromise knob, especially in high-dimensional settings where purely selecting one feature from each correlated cluster can be unstable. It also helps in sparse problems because it can reduce noise by shrinking many small coefficients while eliminating those that add little value, creating a balanced representation. Elastic net can also improve maintainability because it reduces feature explosion without forcing unstable single-feature choices in correlated groups. When you explain elastic net, you are describing a blended penalty that trades between stabilization and selection based on how you set the blend and the overall penalty strength. Ridge is often the preferred choice when many correlated features exist and you want stability, because it handles multicollinearity in a way that reduces coefficient variance without throwing away correlated information. In correlated clusters, ridge tends to distribute weight rather than picking one feature and zeroing others, which can produce more consistent behavior across retrains. This matters when you want a reliable model that does not change its explanation dramatically when the training window shifts slightly. The exam frequently tests this scenario by describing many overlapping measurements or derived fields and asking which regularization approach helps, and ridge is often the most defensible answer when stability is emphasized. Ridge is also useful when every feature represents an important business concept that you do not want to drop because it keeps all features in the model while reducing their extremes. The trade-off is that ridge does not produce a sparse model, so interpretability can remain challenging if you have many predictors, but the predictions and coefficients are often more stable. When you choose ridge, you are choosing smooth constraint over hard selection. LASSO is often preferred when you need a simpler model and feature selection, especially when operational maintainability and governance require a short, defensible list of drivers. If you must minimize the number of required inputs, LASSO can help by zeroing out low-value predictors, reducing dependencies, and simplifying deployment. LASSO is also attractive when you have a very high-dimensional feature space because it can cut the feature set down to a manageable size, which can improve stability if many features are weak. The exam expects you to understand that LASSO's selection is sensitive when predictors are correlated, so if the scenario includes heavy multicollinearity, pure LASSO can create instability in which selected feature changes across runs. In such cases, you may still choose LASSO if selection is the priority, but you should validate stability and consider grouping or elastic met if selection becomes erratic. The point is that LASSO is a governance-friendly knob when you want a model that uses fewer features, but you must ensure the resulting sparsity is not brittle. When you choose LASSO, You are choosing interpretability and operational simplicity as primary goals. Penalty strength must be tuned using validation, not training performance alone, because the penalty determines where you land on the bias-variance trade-off. If you tune only to training loss, the optimizer will prefer weaker penalties that allow more fitting, which often increases variance and reduces generalization. Validation tells you whether the penalty is improving out-of-sample performance, which is the real test of whether you are controlling overfitting effectively. The exam expects you to tune with honest evaluation design and to avoid peaking at test outcomes. Because penalty tuning is just like hyperparameter tuning, it must not leak into final performance estimates. Penalty tuning should also consider stability, not only average score, because a penalty that slightly improves a metric but increases variance across splits may not be a true improvement. In many systems, the best penalty is the one that produces stable performance across segments and time, because that stability is what supports deployment trust. When you tune penalty strength properly, you treat regularization as an evidence-driven control knob rather than as a default setting. Too much regularization increases bias and hurts fit because the model is forced to be so simple that it cannot represent real relationships, leading to underfitting. This shows up as training performance falling significantly and validation performance not improving or also worsening because the model is being constrained beyond what the data supports. You may also see residual patterns reappear, such as curvature or segment bias, because the model lacks capacity to capture structure. The exam expects you to recognize this symptom because it demonstrates that regularization is not a free improvement. It is a trade that can be overdone. Too much regularization can be tempting when you fear overfitting, but if it collapses the model's ability to learn, you end up with a stable but wrong model. The key is to find a penalty that controls variance without eliminating meaningful signal, which requires validation evidence. When you describe too much regularization, you are describing the bias side of the control knob being turned too far. Too little regularization increases variance and instability because the model is allowed to assign large coefficients based on limited evidence, especially in high-dimensional or correlated feature spaces. This often produces strong training performance, but weaker validation performance, and it can produce coefficients and feature importance that change across retrains. In deployment, too little regularization can cause brittleness under drift because the model is tuned to specific quirks of the training period and responds poorly when distributions shift. The exam expects you to recognize that weak penalties are a common cause of overfitting in linear models, especially when features are numerous and overlapping. Too little regularization also increases sensitivity to noise and outliers because large coefficients amplify the influence of extreme or noisy observations. The practical remedy is to increase penalty strength until validation performance and stability improve rather than chasing training perfection. When you describe too little regularization, you are describing the variance side of the knob being too loose. Regularization selection should consider interpretability and governance needs because the best approach depends on whether you must explain coefficients and maintain a stable set of features. If governance requires a short list of drivers and minimal feature dependencies, LASSO or elastic net may be preferred because they can reduce the number of active predictors. If governance requires stability and defensible behavior in the presence of correlated features, ridge or elastic net may be preferred because they reduce coefficient variance and avoid arbitrary selection. Interpretability also includes explaining that regularization changes coefficient magnitude, so coefficients should be interpreted as conditional on the penalty and the scaling of features, not as pure causal effects. The exam expects you to make these connections because it tests not only algorithm knowledge, but also the ability to choose methods that fit organizational requirements. In many real deployments, stability and auditability matter as much as raw performance, making regularization a governance tool as well as a statistical one. When you choose regularization with governance in mind, you are designing for sustainability.
Regularization is tightly connected to the curse of dimensionality and sparsity problems because high-dimensional feature spaces provide many opportunities to fit noise and many weak features that can receive misleading weights. In sparse settings, many features are rarely active, which makes their estimated effects noisy, and regularization reduces the chance that rare features receive extreme coefficients based on a handful of examples. In correlated settings, redundancy inflates coefficient uncertainty, and regularization reduces that instability by shrinking coefficients and limiting sensitivity. The exam expects you to recognize regularization as a primary mitigation for these structural data conditions, not only as a remedy after you see overfitting. Regularization is also a practical alternative to heavy feature selection when you want the model to decide how much weight to assign, while still being constrained from extreme choices. This is why regularization appears so frequently across model families. It is one of the most general tools for controlling variance. When you connect regularization to high dimensionality, you show that you understand why the knob exists.
A helpful anchor memory is ridge stabilizes, LASSO selects, elastic net balances. Ridge stabilizes by shrinking coefficients without eliminating features, which is useful for correlated predictors and stable behavior. LASSO selects by driving some coefficients to zero, which is useful for simpler models and feature reduction when governance demands it. Elastic net balances by combining shrinkage and selection, which is useful when you want sparsity without unstable single feature selection in correlated clusters. This anchor helps on the exam because it maps each method to its primary behavior and typical use case, allowing you to choose quickly based on scenario constraints. It also prevents a common mistake where people treat all regularization methods as interchangeable when their practical effects on feature sets and stability differ. When you use the anchor, you can justify your choice in one sentence, which is often all the exam needs. To conclude episode 80, pick one method for a scenario and explain why, because scenario-driven selection is how the exam tests these concepts. Suppose you have a data set with many correlated telemetry features that measure similar aspects of system load, and your goal is stable prediction with consistent behavior across retrains rather than aggressive feature elimination. Ridge is a defensible choice because it handles multicollinearity by shrinking coefficients smoothly, reducing variance, and preventing unstable sign flips while keeping all the conceptually important features in the model. You would tune the penalty strength using validation, watching not only the primary metric, but also stability across time windows and segments, because the goal is generalization and reliability. If the organization later requires a smaller feature set for deployment simplicity, you could consider elastic net to introduce controlled sparsity while maintaining stability in correlated clusters. This reasoning reflects the core skill. Choose the regularization knob that matches the data structure and the governance goal, then tune it with honest validation rather than with training performance alone. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.